Hello, everyone. Welcome back to the AAS YouTube channel, and this is part of the good stuff. This is the AAS Journal Author Series, and I am super happy to have Oscar Fuentes-Muñoz with us today. Hello, Oscar.
Hi, thank you for having me.
Well, thank you so much for getting to talk about your very awesome article. It's very cool.
I'm glad you find it.
Yes,
No.
other people do too. And Oscar, where's your wave function these days? Where are you located at?
So I'm actually in Southern California. I did defend my thesis as of last month. So yeah, I'm warming up already to the next step. I will be joining as a NASA postdoctoral program fellow at JPL.
Cool.
So,
Cool. Well, congratulations,
yeah.
Dr. Oscar.
Thanks.
Very
Yeah,
awesome.
still getting used to it. Yeah.
And it probably is a little bit cooler in the LA area than it is here in Phoenix, where I'm at on this August 8th of 2023 as we record this. So we are a little cooler today. Got a little rain this morning. The clouds are coming in, but probably still a little bit warmer than LA. So.
Oh yeah. So has the power switch turned on already of the heat in Phoenix?
Yeah. Power switch went on about 3-4 weeks ago.
Okay.
Stayed on. So one of the things that we haven't gotten this year so far usually is when July and August are when the rainy season happens, monsoons.
Oh, gotcha.
Really gotten a good one to cool it off this year. So we've had this, heat dome over Phoenix, sort of poster child for this stuff. So
yeah, I was actually in Phoenix like before the Asteroids and Comets and Meteors conference in June, and I thought that the heat was already on, but I guess maybe not.
You're just warming up. Very cool. Very cool. And Oscar, what do you like to do for research?
So I like to study asteroids, in particular the ones in the inner solar system, and that goes well, especially dynamics. There's lots of cool things that happen to them. They get warmed up by the sun, spins them up, accelerates them. They face the planets and encounters, and that changes everything about their physical properties. So yeah, I like to study that both for planetary science, but also for planetary defense to know which ones are more hazardous.
Right. And we have moved one recently. We have moved.
Yeah.
Start.
Oh, yeah.
Cool. Yeah. And that is going to bring us to this very awesome AJ article. It is open access, people. It's the open access era. Go get a copy for free. Go grab one. The hazardous kilometer-sized NEOs of the next 1,000 years. And Oscar, take us away.
Sure. So, well, usually when we kind of look at how hazardous asteroids are once they discover them, the impact monitoring systems look at them for about 100 years, maybe a few hundreds of years, because that's usually for how long into the future we can tell where the asteroid is exactly going to be.
Okay.
So that's the second part of the title. The first part is why the kilometer-sized NEOs. That's the first group of interest that we looked at as of the US congressional request to NASA to actually tell, well, we need to find these ones and then where they are, discover them all. Because that's like the first effort in planetary defense is to discover them. Like they're still, especially as you get to smaller asteroids, we still have a lot of work to do to complete that population. Yeah. But the kilometer-sized population is actually pretty well characterized. Cool. We believe we know about 95% of them.
Okay.
And good. And the orbits are also, we have good solutions about those. So that's why we decided to ask the following question, which is, can we actually push those hundreds of years further into the future, and how can we look at that? So that's those are the methods that we present in this paper applied to the kilometer-sized population.
Cool, very cool. Okay.
Yeah. So the way that we do this is by understanding that we can split the conditions for a condition in two. The first one is looking at the minimum orbit intersection distance, or MOID.
Okay.
So that's a parameter that I'm going to be talking a lot about. And it right now it is a constraint to define a potentially hazardous asteroid. So we filter the asteroids, and if this MOID is more than 0.05 astronomical units, and they are also large enough, then, well, this asteroid is a PHA. It's potentially hazardous.
Okay.
But a few years ago, really, we started looking, and this was work at CU Boulder with my advisor Dan Shears, and also collaborators at JPL with David Farnoki and Ryan Park from Solar System Dynamics.
Cool.
And together with them, we started looking at the fact that this MOID, the distance, is actually not constant over time. As the orbit changes by the influence of the planets mostly, then this distance is going to either increase, and then the asteroid is less hazardous, or just decrease and get closer to the Earth, and then it means that we need more information to know what's happening.
Yes, one step.
Because
yep.
Yeah. So that's the first condition that we need for a collision, is that the MOID needs to be close to 0 or very, very small. That means that this ellipse in which the asteroid is and the ellipse in which the Earth is, those intersect. Now, once those intersect, you need the timing to be right. So the asteroid and the Earth need to meet at this intersection point at the right time, at the right place.
Right.
And this already takes us to why is it useful to study and to split this approach into, which is the growth in uncertainty.
Okay, right, yeah.
And we can already see this. Figure 1 is already an example of this.
Let's take a
yes.
And
thank you.
Thank you. Okay, let's blow that up a little bit.
Yes, so this is a Monte Carlo simulation of the orbit of an asteroid, of a kilometer-sized asteroid. And what we do, well, sample a few examples from the uncertainty distribution, and then propagate for thousands of years. And what happens is that the uncertainty in most of the orbit elements actually grows much slower than the uncertainty in mean anomaly, which is where within the orbit you are.
Okay.
So you can see this in the top 6-pack of figure. You have the orbit elements, and then the uncertainty, the uncertainty doesn't grow as much, except for mean anomaly, that after a given date, it becomes completely unknown, which is this kind of, m minus m not.
Yeah, we go along for a while, and then.
Yeah, exactly. So that translates into the MOID, the minimum orbit intersection distance. And because the MOID is independent of any of the past angles, because you're finding that as the minimum distance between any of those 2 points, so you're solving that optimization problem.
Yes.
That means that the uncertainty in the MOID actually will not grow as much as the mean anomaly.
Okay.
And then we have a larger confidence into whether or not the first condition of the collision is held for longer into the future than those hundreds of years that we initially stopped our analysis in the impact monitoring systems.
So what are the different colors? We got black and a bunch of colors.
Sure. So each one of the colors is one of the Monte Carlo simulation runs.
Okay.
And then in the black solid line, what we have is the nominal one. So the nominal solution that we have in the orbit.
Okay, got it. Cool.
And another interesting thing that we see here is that in the inner solar system, one of the main characteristics is that we can have planetary close encounters, and those can make great changes in the orbit. And if you look at the same major axis, which is the top left of the figure, the nominal actually sees like one planetary close encounter that creates like this large change.
Very cool. That happened at about 4,000 years or so. Okay. Boom, boom, boom.
Yeah, exactly. And you can
Right.
actually look at the bottom left figure, the Earthmoid, because we also care about the moid, because once the moid with one of the inner planets, especially Earth or Venus, becomes small, the uncertainty can grow a lot. It's because you're starting to find planetary close encounters that might not be as close as to worry about a collision, but they start to create these changes in the orbit that start to build up, that are larger. And that's actually what we find here in the bottom two, that we find a close encounters with Venus that actually right before these 4,000 years start to increase like the uncertainty of this statistical distribution.
Right. And just to be clear, the driver of the uncertainties is the changes in the orbital, in the state vector due to planet perturbations. Yes.
Yes, that's correct.
I'm good. Okay.
Sure. Yeah. Thank you. So that's all of the orbital dynamics background that you need to understand this paper. So we can move on, and that's most of what we talk about in section 2. But if we go to figure 2, we can actually see how these effects translate in the dynamics of the moid.
And just for fun, what is your n-body integrator?
So this is actually, we're using the orbit propagation tool that they use at JPL.
Okay.
So same as Horizons, if people are familiar with that. And we, whenever there was a Yarkovsky acceleration significantly measured for these asteroids, we included it also in the model. So just since you ask.
Yes, thank you.
Yeah. So what are some of the kind of dynamics of the moid that we usually find? Hopefully figure 2 gives some examples of that.
Yeah.
And in the top, you see some cases in which, well, as we were introducing earlier, the uncertainty in the whole orbit doesn't grow much for thousands of years. So we have a lot of confidence into making predictions. And one common situation you find in the top right, in which this asteroid, this 1950 DA, actually, as the orbit is pulled secularly, mostly by Jupiter, then it gets the Earth moid goes to 0.
Yes.
And then increases again, and then goes
bang.
Yeah.
2 of them.
Exactly. So this is a very frequent pattern that we find. And this is really what we care about. If you think earlier about the first condition to have a collision, this line needs to be near 0 such that a collision is possible.
Right.
And even if we can provide for thousands of years, this is the actual small window of time of maybe 100, 200 years in this example, in which a collision is possible. So that's the window of time that we actually care about. Yeah, exactly. You're already pointing to other situations in which, if this uncertainty grows, then this window is not as well determined.
Right.
And that means that we need to work a little bit harder and look at the asteroid for longer windows of time. And the bottom right is also an example in which, we are seeing like more complex dynamics than just this linear secular drift in the moid. So even if we have this, because there's this couple dynamical effects, this window might not be just this, the bottom of the B's or W's, but it can be longer windows of time.
Yeah. Just out of curiosity, what are the sources of the largest uncertainty that is driving the patterns? Is it semi-major eccentricity? Because we can't observe all the state vector, right? So
so there's a few points. First, it's our initial uncertainty, and then where we are within the solar system, because that will also define the kind of perturbations. So say major axis, the value, but also the uncertainty in that, as you're saying, is usually the most important, because then as that increases, then the timing becomes like, one good model to model that is called the line of variations, in which we model like this, the location of the asteroid along this line because of this uncertainty in same major axis.
Okay.
But yeah, so those are the main drivers, and then there's these other the perturbations acting on the orbit. Like the stronger those are,
the more it gets. Very cool.
Yes.
I'm with you. I'm good.
Perfect. Sounds good. So if you're with me, then what we actually did is to define this new metric to quantify whether or not how hazardous the asteroids are going to be. And this is similar to computing a probability of collision. And yeah, if you see the equations of the next page are actually
I like equations. Okay.
So in some models, yeah, we can start by equation 3, really.
Okay. Probability, then we got gamma, and there we go.
Yeah, so we'll go back to equation 1.
Okay.
So this metric, to characterize how hazardous they are, has like two parts, which is assuming that you can split it into independent probabilities.
Right.
One is the probability that the moid is small, which you can compute or estimate by this delta t of moid being smaller than a distance threshold. Okay. So that will give you the first estimate, and this is something that we can measure from the Monte Carlo analysis. So we propagate a bunch of them, and then we measure these windows of having a low moid.
Okay.
The second part is the PMA, is the probability that the mean anomaly is right, or the probability of the timing. And in general, there's a few works from the really last century that already go from the OPIC, Weatherhill formulas, that really tells us that if you assume a uniform distribution for the mean anomaly, and that the orbits are intersecting, or then you can translate that into a probability that there's a collision.
Okay, I'm with you.
So we combine these two, and then with a few Monte Carlo samples, we estimate the first part, and then these will allow us to rank the kilometer-sized population. And the first, well, the disclaimer I have to introduce is that this is not a rigorously computed probability of collision, because that's the work of using the tools of the impact monitoring systems, very rigorous, tens of thousands of Monte Carlo samples, and then from there you obtain a collision probability. But using this metric, you can compute it fast, you can sweep through your population and sort them by the implicit risks. So this tool gives you homework. This tool tells, hey, these ones you need to look closer, because the moid is small, or because its orbit intrinsically has a higher probability of collision. Maybe because the encounters are very slow, and maybe, so all of these characterized by the second part of the expression.
Yes, cool, very good. I'm with you.
And that takes us to the results, and we have two parts. The first one, we wanted to start by looking at, well, how many of these asteroids will actually have a low moid for a long period of time.
Okay, yes.
Which is a different question from which ones will have a larger intrinsic probability of collision.
Okay.
But having a low moid means usually that you will be able to maybe observe it more, because you'll have like more opportunities to gather observations. They might be good opportunities for mission exploration. So this already could be a valuable feature. So that's one of the reasons why we first aim to answer this question.
Okay, cool. Yeah,
and if we go to figure 3, that's, well, we can already start to see how many of these kilometer-sized NEOs we're going to be having a low MOID, in this case defined as being smaller than 0.01 astronomical units.
Yes.
And for as many as we have discovered, because we have very good solutions of their orbits, we are already very confident in the numbers for a few hundreds of years. But then, because for a few of them we have some uncertainty, as we go into the future, there's this number actually increases, and these are the beans.
Right.
And so yeah, this is a first snapshot. It gives us rough numbers. Well, we see that there's around 40 kilometer-sized NEOs in the next centuries that will have this low MOID condition.
That's a lot.
Well, yeah. So to complement that point, and the reason why I sleep nicely at night is that even if we are doing all of these studies, well, there's many reasons, but one of them with respect to hazardous kilometer-sized asteroids is that the background probability of an impact is still every few million years. It's around that order of magnitude.
Mm-hmm. Okay.
So we are doing our due diligence of finding which ones we need more information about, but there's still not like a high risk associated with any of the objects. So yeah, it might sound like a lot, but it's actually
well, I meant a lot of, I think in the beginning you said that there was 800 known.
Yeah, 850.
800, right. So 5%.
Yeah.
Mm-hmm.
I guess if you put it that way.
Yeah, 5% are worth watching. Okay.
Yeah. So the next kind of complementary question is, well, for how long do they stay within this low MOID condition?
Yes.
And table 1 summarizes, or it's the snapshot of what we found in figure 4. So I think it's maybe more interesting to go that way.
Let's go to figure 4 first. Ooh, whoa, wow.
Yeah, it's a big one. So this, and it's same format as a letter figure. This is a list of asteroids.
Mm-hmm.
And then we show whether or not the low MOID condition is held, and for how long. And if it is held, then we show the information in that line of each asteroid. Mm-hmm. And then the color bar is actually the agreement within all the Monte Carlo runs.
Got it.
So we have the nominal plus 20 samples of the uncertainty. So that's all of the continuous black lines basically tell us, well, this is unanimous among all of the Monte Carlo samples.
Yes. Okay.
And something interesting, if we recall the previous examples, we see that a few of them we're seeing like small windows in time.
Yes.
But we start to see that there's some continuous black lines. That means that those asteroids are actually experiencing a low MOID for hundreds of years.
Yeah.
Which means that window is actually much longer than maybe we could have thought earlier.
Okay. Mm-hmm. Mm-hmm.
So these are, well, this is, in case you're wondering, this is sorted by, you see, starting from the bottom left, the first date in which we find the low MOID condition. So the bottom of the list is the ones that, well, the 40 ones that we found earlier, and then it goes on as we find more and more kilometer-sized asteroids with that condition.
Cool. Very cool. Great pot.
Thank you. Yeah, it's we needed to get like those letters small, but
yeah, your font is going to be an issue as you get more and more of these.
But the idea was that, if you are looking at a kilometer-sized asteroid and you pull up this paper, you can Control F the name and you can pop up, hey, actually we looked at the low MOID and you can see that information there. So that was the
yeah, it's a great
the idea.
Mm-hmm. And for those who must have a table, there's 10 of them. Mm-hmm.
Yeah, there's a subset of the table. We give more details about the once we take into account this intrinsic probability of collision.
Okay. Okay. Very cool. Very cool.
Which takes us to I guess figure 6.
Sure.
Is that ready?
Let's go to figure 6.
I think it's really the main result.
Money shot. Here we go. Okay.
And in this case, for this second part of the analysis, we say, well, now that we know that whether or not the moid is going to be small, let's try to use this metric for how hazardous they are.
Okay.
And not only we're going to use this formula, but we're going to take into account that we actually know the position of the asteroid for hundreds of years, right?
Mm-hmm.
So we use the standard deviation in mean anomaly, which is the color code of this figure, to actually tell us whether or not the position is very well defined, which is this orange color.
Mm-hmm.
If the uncertainty is small, we know perfectly fine where the asteroid is.
Okay.
Once it increases, you see standard deviation in the order of 2 digits, so hundreds of degrees, so completely unknown.
Yeah.
In that case, we can use our expression, because if you remember, one of the assumptions was that the mean anomaly had to be uniformly distributed.
Yes.
So this will tell us whether or not we can trust that assumption to use the expression. And it will also allow us to discard the risk for asteroids in which, well, the moid was small for a very long period of time, but we knew perfectly where the asteroid was, which means we looked at the track of close encounters and we didn't find any that was very close or concerning, so we could discard that asteroid.
Okay. I'm with you.
So that's why we combined the information of the uncertainty in mean anomaly with the low moid information.
Yeah.
So in this figure, we show only the standard deviation if there was a low moid. So that's the condition to show it. And we can already start to rank this population.
Okay.
And a few interesting findings. The moid is shown only if it was smaller than 0.01 astronomical units.
Yes.
And which I think from top of my head, I think it's 60 Earth radii.
Something like that.
So you can see that here on the top, the first case, which is 1994 PC1, was actually something that surprised us, because this asteroid, and will be analyzed in more detail later, this asteroid actually has a low moid for thousands of years. Yeah. Which is further than we can tell exactly its position. So you can already see that by the color of this line. Right. And 2400. Okay. Yeah. So we know exactly where it's going to be for about 500 years. So the risk in that time is 0. But it's definitely one that we want to observe further, so that we keep on watching it, and then we will keep on driving this probability to 0. Right. This is usually the same philosophy. It's not exactly the same, but the same idea that once an asteroid is discovered, we have only a few observations, and then the uncertainty is large. And within that, the possible orbits and trajectories, there's sometimes a few that could be a collision with the Earth. Right. However, most of the time we get more observations, narrow that uncertainty down, and then discard the risk. Right. Or at least reassess it. Yeah. Fun fact, it's been like 7 times so far. We actually narrowing down the uncertainty actually led us to say it's actually going to collide with the Earth. So we were able to predict a collision by a small boulder. So, much smaller than the asteroids of this study, and, even recover meteorites. So, that's very cool. Really? Yeah.
Wow.
Anyway, going back to the paper. Sorry
Okay.
about that.
It's all good. Sidelines are good. It's extra bonus material. There we go. That's what you got.
Yeah. Anyway, so going back to this, we have other interesting asteroids that we highlighted using this method. And that's what we cover in the rest of the paper. So the next section is, well, looking at a few interesting asteroids. By the way, the results of this figure are also in table 2.
Yeah. So let me ask one question here.
Yeah, sorry.
Why are there blank sections, I guess I would say? So we go blank and all of a sudden we know what's going on. And then maybe it's on this one, on when we observed it. But then it goes away. We don't know anything and all of a sudden it's black.
So that means that the MOID wasn't small during those dates.
Got it. Yep. Okay.
So it's actually a very good question. So this case, 4183 QNO has a low MOID window between 2200 and for maybe 200 years, roughly. But we know perfectly well the position in that window.
Yes.
However, in its next window, by the end of the millennium, then we are not so sure. So that's just the two windows and the uncertainty in the position in both.
Very cool. Okay. Good. Thank you.
So table 2 summarizes the results of this figure with this estimated with this estimated probability.
Didn't want that. Okay.
That you can.
Let's see. We got period. Delta T over T. There's your timing metric. Incoming in. Okay.
And actually, the top 8 is actually featured in figure 7. So you can already look at those. And
figure 7. Okay, let's zoom in a little bit on these 7.
Yes.
Okay.
So with this information that I was telling you that we included now, that is the uncertainty in mean anomaly. So the red dashed line that you showed, so each subpanel is an asteroid. And for each one of those, this vertical red dashed line indicates an increase in the standard deviation in mean anomaly, when it's larger than 10 degrees.
So here's the red dash line. Okay.
Yes. So we don't find it for all of them. That's why you don't see it in all of the figures. But
got it. 1, 2, 3.
Yeah, exactly. And then we also have additional information in these figures, which are the actual close encounters that we found in the propagation.
Okay.
So that's the scatter plot that you see on top. The lines are the same that we were seeing earlier, which is the Earth MOID. And then each one of the colors, each Monte Carlo run, and then in black, the nominal propagation.
Okay.
And then you see some of the circles. There's a lot of information, lots of things going on. But the close encounters that are circled with a red circle on top, those are below the lunar distance.
Okay.
So much closer. Sorry, the lunar distance is 60 Earth radii. That's the
inside that orbit.
Yeah, that not 0.01. That's much larger. And yeah, so this is you can see for a few of these examples a little bit of what we were saying earlier by understanding the dynamics, right? You see, for example, the example of 5011
PTA.
That you see the MOID is going to 0 and then
bounce out.
Yeah. And then a little bit before that, the uncertainty increases and we have some close encounters. But actually at top of the list, we have examples in which there's some more interesting things going on. Okay. And you can see that, for example, for PC1, as I was saying earlier, there's this continuous low moid period, but there's also Tutatis, which has these oscillations near zero.
Yes, yes.
Which, becomes, in this case, the uncertainty, the whole orbit becomes like larger, because you can see that each one of the Monte Carlo runs is also doing its own trajectory, right?
Very cool.
So, yeah, lots of things that we could unpack from these experiments or these dynamics, but we already unpacked a few of them for the reader.
Let me ask 2 questions.
Ooh,
We have a
sure.
purple curve on some and a light blue curve on some, but not all. So what does the purple curves and the teal curves mean?
So each curve is going to be one Monte Carlo run.
Got it.
So each one of these has its own Earth moid, increasing, decreasing, doing these oscillations. It depends on the.
It corresponds with that. Okay.
It's one fictitious asteroid.
Gotcha.
And then the circles match the colors with each Monte Carlo run.
Gotcha. I'm with you. What's going on here with Mashup? Mashup. This is the one we saw where all of a sudden it just goes
So
crazy after 1,000 years.
Mashup, I think it's kind of a personal favorite.
Ooh, okay.
Because it actually featured later on, and we can go to figure 10 just to kind of zoom in on what's going on.
Yeah, let's go to figure 10. 8, 9, 10. There we go. Mashup. Okay.
Getting there. Yeah, there you go. So this one, well, first of all, it's having resonant encounters, which means that there's a relationship between the same major axis of the Earth and the asteroid, such that every 17 or 18 years, you have a very close encounter. Or a close encounter. And that's why you see like as many frequently and equally spaced, or roughly equally spaced. Right. It's because this resonance between the orbits.
Yes. Going down, 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 down.
So that's one first cool fact. The second one is that the Earth moid is drifting to zero. So by the end of this millennium, it's actually going to start experiencing closer and closer flybys with the Earth.
Yes. And the amplitude's getting larger.
Yeah. And not only that, but this is actually, and goes a little bit beyond. Second fun fact is that this Moshap is actually a binary asteroid. And both of them are actually quite large. And so, if this was if we were now at year 3000, we'd actually be so excited about this, because each one of these flybys can disrupt the orbits of binary asteroids. Can change the dynamics, and lots of funky things can happen to binary asteroids when they close to planets.
Absolutely.
So this might be the case for Moshab, in which it seems pretty likely that it will have flybys below the lunar distance.
Now there's a prediction. That's a fun fact. Okay. We'll check with you in about 1,000 years.
Yeah, cool. Exactly. Cool. I'll leave something written like in maybe my tombstone or something.
Yeah, look at that. You'll get a citation in 1,000 years.
Yeah, hopefully.
Very cool. Yeah, very cool. Very cool.
Okay, so yeah, other important, or I guess, at least examples that have been featured in the literature earlier. This, you don't have to move further. It's already figure 11. Okay. And this 1950 AD was actually found to be experiencing a close encounter in this year 2860. That, we still have quite some uncertainty in the position. So in an actual very, very close encounter cannot be discarded. But so, it was interesting to see it pop up, because this was already known that this was going to happen. And indeed, we actually found that this is that this encounter is happening, and that it's in our list of it will have a low moid, and then we will need to gather more information about its orbit to be able to completely rule it out. But you know, that's still a few hundred years from today. So
we got some time to figure it out. Okay.
Yeah, we might have other ones more interesting to figure out before that. So
cool. Very nice.
And yeah, the last one was 2022 AP7 because it was already in some news last year.
Yes.
Because right now, as I was saying, we have a very large completeness in this population. So every time that we find a kilometer-sized asteroid, a new one, well, it can make people wonder, like, hey, this is actually a pretty big one. So what's going on? And we know what's going on with this one for, you know, a long time, hundreds of years. And even though it will have a low moid, its position is very well known through that window. So there's this window of time that, yeah, you're already pointing to it in the 100 years from now.
Yeah.
But yeah, no risk of encounters. Few resonant encounters in the past, which is what you see in the left panel, but that's also shown there.
Cool. Yep.
And yeah, if you don't have any other follow-up questions, I was just going to say that we have an appendix that has the orbit elements evolution of all of these individually analyzed asteroids. So in this later section, you have the orbit element histories, which tell you a little bit why you see what you see on the moid. And this is to provide more context to understand, well, which are the dynamical effects that might be affecting these asteroids.
Very cool. Very nice. Very nice. Oscar, thank you so much for walking us through your very awesome HA article. Very cool.
Thank you.
Thank you. And you touched on it a little bit, and so I'll push on it a little bit. So where do you think we go from here, given the published article? Are there yet more observations of kilometer size? Do we start moving down in the size distribution to more fully characterize? Is there additional theoretical work to be done? Just so sort of next steps on where we go over the next couple of years on this topic.
So once you go to smaller asteroids, so yes, you were pointing in the right direction. We are going to find more often that well, the orbit solutions might not be as good. So we will be having to define some well, way to classify whether or not how hazardous they are, because we know that kilometer-sized asteroids, all of them are, you know, in case of a collision, but for smaller ones, like that will depend. So basically, we're going to be able to, yeah, to distinguish a little bit between those situations, considering more the uncertainty in the orbit. That being said, that's on the side of you know, the dynamics side of the analysis. But on the observation side, there's few surveys coming up that will really increase a lot the population that we have of PHAs and in general of all asteroids.
Cool.
The Beta-Rubin survey, the LSST, NEO Surveyor is also going to help a lot. So among all of those, we're going to have more work, which is nice.
That's good. Very cool. Very cool. Oscar, thank you so much for walking us through your very lovely article.
Thank you. Thank you very much for the interest and having me.
Sure. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Bye.